Let's talk about electric power. Electric power is a very fundamental quantity and often is confused with energy. So let's try to make a little bit of clarity. Here we have the definition. As you can read here, the electric power is the rate at which the energy is converted from electrical energy of electrons to other form of energy. So let's remember the energy is the capacity to do some work. So when you have a certain amount of energy in a battery, that means that if you connect the battery to a circuit, you can actually accomplish some work, whose value will be equivalent to the energy stored in the battery. And the power is measuring the rate at which the work is done. The power is telling you how quickly you're consuming the energy that is stored into your battery. Let's now try to calculate the relationship between power and voltage and current. Right now, this is the first time we have seen power, the concept of power. We are familiar with voltage and current, and we wonder if there is a relationship between them. So let's try by defining again the current and the voltage. So the current can be written as the number of electrons multiplied by the charge of the electron divided by the time. So again, you can imagine sitting by a wire, looking at a section of a wire. There will be a net amount of charge moving in a certain direction, so a net amount of electrons moving in one direction. You multiply the number of electrons by the charge of one electron, so you get a certain amount of charge that move in a certain direction across the wire during a certain time. Then you divide that by the amount of time that the charge has taken to pass, and that is the value of the current. Now the voltage, as defined in the past, is the electric potential energy per unit of charge. So if you have a certain amount of electrons sitting into a wire, they're going to have a certain electric potential, and you just then divide by the total charge. So now you have the energy per unit of charge. We can also rewrite this as U divided by number of electrons multiplied by the charge of the electron. Now, if you multiply V by the current, what we obtain is very easy to calculate, because you'll see immediately that these two, the numerator here and the denominator here, they will simplify. And so what you will obtain at the end will be just, the energy divided by the time. So multiplying the voltage by the current into a certain wire, it gives you the change of energy with the time. This is exactly the definition of electrical power, which is the rate at which the energy is converted or transmitted. So we can call this P, and the unit of measurement is the watt. Let's talk a little bit more about the definition of electric power. So the electric power is the rate at which the energy is transferred from one system to another, but also the rate at which the energy is converted from electrical energy to other form of energy. So this can be a little bit complex to understand. So I wanted to give you an example, in particular of conversion of energy from electrical to thermal. This is something we already discussed in the past, but it's good to bring it back now that we have discussed power. So a resistor, as indicated down here, now we move to this definition, inhibits the flow of current in a circuit. The larger the resistance, the more difficult it will be to have a current through it. In fact, energy is required in order to have a current going through a resistor. Energy, which in electrical circuit is usually represented by a voltage, as the voltage is a representation of electric potential energy. In fact, if we have zero voltage, we also have zero current. There's no energy available to have an electron go through the resistor. Now, the interesting thing here is that in the case of the resistor, the energy is dissipating, heating the resistor itself. So as the electrons are pushed through the device, through the resistor, as we discussed at that time, they will bounce against the structure of the resistor, against the lattice of the resistor, and they will convert their electric energy into thermal energy. And the net result of this is that the resistor temperature will increase. Now, let's calculate what's the power that is dissipated on the resistor. And in order to do that, we just reuse this fundamental equation that we just calculated here, and we apply that for the case of the resistor. For a resistor, well, we have V multiplied by I, and now what we can do, we could replace I with another equation from the Ohm's law. So V is also equal for a resistor of V divided by R. So now if you write it this way, we can say that This is also equal to V squared divided by R, and this is equal to the power. This equation can also be written in another way. Instead of replacing I with V divided by R, we can replace V with I multiplied by R. So in that case, this is equal to I squared multiplied by R. So these are two identical equations. They give exactly the same result, and the power that is dissipated through a resistor is the rate at which the electrical energy is converted from electrical of the electrons into thermal energy. Let's try to understand the difference between power and energy with another hydraulic example. So here we have a little system with a cistern. Cistern is a big tank full of water, and this big tank is at a certain elevation compared with the turbine, and let's call this different in height h, and let's say that is equal to 100 meters. Then we have a valve that can be open and closed, so allowing the water to flow down through the turbine, and the turbine is just a device that can be used to convert the energy of the water into electrical energy, for example to power a house. Now let's do a little bit of a calculation to see, first of all, what is the energy that is stored into the cistern. As we've seen before, because we have a certain amount of water with a certain mass at a certain elevation, that is equivalent, that means that the water will have a certain potential energy, in this case gravitational potential energy. So here we have a few numbers, let's just do the math. So we have been told that the volume of the cistern is 10 cubic meters. So as a consequence, because this is water, we have a weight of 10 tons, so 10,000 kilograms. So now the energy, U, it's equal to mgh, where g is the gravitational acceleration, which is roughly equal to 10. So if you substitute, so the mass is again 10 ton, g is about equal to 10, and h is about 100. So in the end, what you get is about 10 megajoule. So this is the energy that is stored into the cistern that can be used to produce a certain amount of work. The way you produce the work in this case is by opening the valve, letting the water flow down, and turn the turbine so that the energy can be converted into electric energy. Now let's say we have a certain flow of water that is equal to 1 cubic meter per second. So when you open the valve, you have 1 cubic meter per second of water coming down. So now in this way we can easily calculate what is the power that is transferred from the water to the turbine. So we have 1 cubic meter per second. Now this cubic meter, each of the cubic meter has a weight of 1 ton, and then we can multiply by the acceleration of gravity and the height. So in this case, you see it's kind of a similar equation. We have the mass, we have the acceleration, and we have the altitude, and all of that divided by second, meaning this is an energy that we are transferring every second. So this is equivalent to, if you do the math, 1 megawatt. So this is the amount of energy that is transferred every second from the system through the turbine. So in this case, because we have 10 megajoule and we are delivering a power of 1 megawatt, that means that after 10 seconds all the energy will be consumed. Now on the right I have exactly the same drawing. The system is the same, it's still 10 cubic meter, so the mass of the water is the same, it's 10 ton. But now, as you can tell probably from the drawing, the size of the tube that connects the system to the valve is much bigger. So it's possible for a much larger amount of water to flow down to the turbine. As a consequence, I also increased the size of the turbine just so that it fits correctly the size of the tube, but that is a secondary detail. So obviously, if we do the same math that we've done before, the energy stored is still going to be the same, mgh, so it's equal to 10 megajoule, because we have the same amount of water and we have the same amount of height difference between the cistern and the turbine. But now, because the tube is much bigger, it is possible for the system to deliver bigger power, because just a bigger amount of water is allowed to flow down from the system to the turbine. So now let's say this tube is roughly twice as large as the previous tube, at least in my very simplified drawing. So let's say now the capability, the flow of water can be 2 cubic meter per second. So now this cubic meter per second, each of the cubic meter will have energy of 1 megajoule, and because we have two of them, so we have 2 megajoule per second. So if we have this, the power that is delivered, it will be 2 megajoule per second, which is equal to 2 megawatt. By the way, if I haven't told that before, obviously given the relationship between power and energy, while the energy unit of measurement is joule, J, the power is watt, W, which is equal to joule per second, because as we said, the power is basically a representation of a rate of energy. So it is natural that the unit of measurement, which we decided to call watt, is the ratio between joule and time. But now let's go back to these results here. So we see that in these two examples, we have the same amount of energy. Again, these two systems has the capability to deliver an overall total amount of work, 10 megajoule. Both of them can do the same thing because they have the same amount of water at the same altitude. But in one case, the tube is larger than the other case, so it is possible for the water to flow out of the cistern at a higher speed, and as a consequence, we can generate a much bigger amount of power. Again, this water analogy can be linked to the electrical analogy, where the energy is obviously the energy into a battery. The flow of the water, expressed in this case in a cubic meter per second, is equivalent to the current. The altitude is sort of an equivalent to the voltage. So as you can see here, in these two cases, we are representing a case where we have a battery with the same amount of energy, the same amount of voltage, but in one case we have a capability of delivering a much higher current to the load, which is the turbine, so we are able to generate a bigger power. So you can think at an example where, for example, we have the battery here, it could be 5 volts and a certain resistance R, while in this case we have again 5 volt, the battery is the same, has the same amount of energy, but in this case we have, I don't know, for example, 2 times the resistance, which means that the current that can flow through the system is half the current that can run into the other case. So the power that we are going to deliver is also going to be half.